under what conditions. Okay, so the ratings game for COP and things like ground source heat pumps or air source heat pumps is that you have to be careful about what are the conditions it's rated at. And if I wanted to have a very efficient ground source heat pump, I would assume the water coming out of the earth was always going to be 40 degrees Fahrenheit, and people in the house keep it at 65. That would be a way to get a high COP. And so then you say, my piece of equipment is a COP of 5 at conditions no one will ever use. So it's all these three numbers are caveat emptor, which is Latin for you're going to get screwed. So let's take a look at how we generally do residential buildings. First thing we assume, all rooms have the same conditions, right? We have a thermostat on the ground floor, and the bedroom on the north side is the same as the bedroom on the southwest side. We assume that they actually have the same temperature conditions, and therefore we can use a single point thermostat to operate the heating or cooling appliance. Now we know that that's a problem, and as we've made better building skins, for a while that actually got truer, right? Like it's truthiness kind of thing. So it got to be more true because by putting a tighter skin, especially in peak heating and cooling modes, the difference between the distant northerly bedroom and the very near southwest bedroom with a big window in it was actually closer because the skin stopped the heat flow being as big a factor. But now it's actually tipped to the other side where it's all about whether you have a window or not. It's all about whether you're south-facing or north-facing, and so those assumptions are just wrong. We're just wrong. Now, can we get away with it? Yeah, often. Yeah, works in my place. I got a super insulated, low-load house thermostat, and it works because I have no really big windows. I have an open floor plan. I don't keep the bedroom door closed. Probably too much information. But anyway, you actually get good distribution in the house, and under those conditions it works. But there's many conditions under which it won't work. So there's no ventilation, right? That's a common scenario. And actually consumers often say, yeah, but I have this air conditioner, right? It's moving air around. Is that not ventilation? Back to the toilet with the swirl thing? No. Until you really flush, it's not gone. And so you actually need to have some air moving out of the house or into the house before you have any ventilation or a hope of it. And in air conditioning mode, the relative humidity control is completely accidental. You get relative humidity, or let's just be humidity, the absolute amount of moisture in the air, will be removed from the air in this home if and only if the air conditioner is operating. Step number one. I think that you should make that point clear. Step number two is that it has to be operating for more than, well, let's just say 15 minutes. Could be 13, could be 15, but if it doesn't operate for 15 minutes in a row, water, the humidity in the air that's condensing on the air conditioning coil won't build up to a thick enough level for the water to form droplets, run into the drain pan, and go down the drain. You need two things. Air conditioner has to run, and two, it has to run for 15 minutes or so before you get your first water out. Okay, now let's see how that connects to low-load houses. Well, if we put in a 2-ton air conditioner in a house that has a 1-ton peak air conditioning load, it's actually not going to run that much. And when you look at middle-of-the-road conditions, let's say it is July and the temperature outdoors is 85, it won't take much operating time to cool the house down. So it runs for 5 minutes, the minimum runtime, Lloyd. It runs for 5 minutes and shuts off. So did it remove any humidity? No. It passed test number 1, it ran. It didn't pass test number 2. And you have to get over both hurdles. And in low-load houses, even test number 1 is a challenge. Because the air conditioners are oversized so much, it doesn't, and you make it energy efficient, the air conditioner just doesn't run. And when it runs for short periods of time. And so it's quite reasonable that for the majority of air conditioning hours in places that are not like really hot and humid, like not Texas, not Florida, is that it's quite reasonable that they remove almost no humidity for the entire summer. You could save yourself the cost of the condensate pump. I should probably not say that because there could be a production builder somewhere going, oh, well, there's $100 I could save. But no, you want the condensate pump. You want to remove that humidity. And as houses get more efficient, there is less and less heat being added to the house. And so the air conditioner runs less. Does that make sense to everybody? But it gets worse than that. Did people stop breathing less because we insulated the house? And when they breathe, you realize that your air is humid, right? What you breathe. Did people stop sweating? No. They sweated just as much before you insulated the house as afterwards if the temperatures kept at 74 degrees in summertime. Did pasta stop producing humidity? Pasta. I'm trying to learn how to speak American. Pasta. Did produce less humidity after we insulated the house? No. So every source of moisture in the home, in the apartment, in the nursing home, in the dorm residence has remained the same, but we're running the air conditioner less often. So what does that mean about the humidity levels in the building? They're going to rise. Now, the only thing that we've done to help solve this from being an utter disaster is that we've increased the air tightness at the same time. And by increasing the air tightness, that was in hot, humid climates, or hot, humid weather, was a major source of humidity in the home. That actually has been reduced. So that's a significant gain. And that allows you to be bad for a little while longer. But eventually, when you're bad for long enough, you end up with humidity control problems in buildings. Now, many people know this problem exists in Andes territory or in Texas. Okay, Houston, of course, right? There's the humidity problems in Houston all the time. But now it's also a problem in Boston, New York City, in Chicago. Dorms in Chicago that are LEED rated actually have summertime humidity problems. Actually, not summertime, spring and fall problems with high humidities because the air conditioner runs, but the students keep breathing. Now, the lowest cost solutions don't have the students breathe, not acceptable to the client. So I always give them multiple choices. But that means that we have to completely change this system to provide some form of humidity control. How we're going to do that? Well, the first thing, let me just, in case there's any people who want to say, oh, well, we'll just use natural ventilation. No, you won't. I mean, I just told you that one of the major gains in humidity control was that we stopped outdoor air leaking into the building. Natural ventilation is the problem, not the cause or the solution. It's the reason you don't want a natural ventilation because when you're air conditioning, it's hot and humid outside, right? Isn't that why you're air conditioning? And so opening the window would be stupid. Now, San Francisco is different because it isn't that hot and humid outside, and they're air conditioning when it's cool outside. And so it's okay to open the window. So that's when you can use natural ventilation. But you can't use natural ventilation when it's warm outside and humid outside, duh. I would have thought that was obvious, but it is a routine question we get in bleeding edge design projects who really want to do low energy homes or apartments, or just last week, a dorm residence. We want to make it a really low energy quality space. So comes up, design trick. Can we use natural ventilation? What, in Kansas? Don't you live there? Don't you know what it's going to be like in September in Kansas? I mean, of course you can't natural ventilate. So that's off the table. We have to use some form of mechanical dehumidification to deal with this problem. So the question is, could you also increase the RH in the wintertime rather than increasing the temperature to provide the same level of comfort? Well, not really, because the difference between 25% RH and 40% RH in terms of thermostat setting is almost imperceptible. It's like half a degree or something like that. But the difference in moisture problems related by going from 25% RH to 40% RH in cold weather can be quite significant. I'm talking a zone 6. I mean, if you're talking Washington, D.C., it's like going from 35% in the winter to 50% is not worth any possible energy saving because of the condensation problems that will occur on windows, in attics, on rim joists, etc. So that's why, yeah, adding humidity to those buildings is generally, almost without exception, a bad idea. Usually there's more than enough humidity generated on the inside. So rather than having a wet sponge that goes through water and you blow air over it, you could just have people in the building. And then you get safe humidity levels. So the comment was, Wisconsin, I'd say the same thing will be true in Dakotas, although Wisconsin, you actually built really tight houses. And we experienced this in Ontario in the 80s, in Saskatchewan in the 80s. Tighten the house up, don't provide ventilation, humidity rises, all kinds of moisture problems. It's less extreme as you go further south, but the same thing still happens, is that you actually have a problem. And by the way, the worst problems in climates that are cooling dominated for humidity, again, aren't in the middle of summer, because that's when the air conditioning has a chance of running once in a while. It's actually the swing seasons again, where they don't run the air conditioner because it's 75 outside, and yet they continue to do the breathing thing. Showering, cooking, and all of those things add moisture, but they're not running their dehumidifier, and they only have a limited amount of ventilation, and they can't remove the moisture. So that's actually a real challenge. Okay, so what would be a low-cost way to meet many of the requirements I spelled out? Well, okay, I've got a ducted distribution system that actually provides heat, cool, and or fresh air into every major space in the building. So you put a duct into every room, and in that duct, we can share the duct work for ventilation at the same as we can use it for heating and cooling. I think this is a building science insight on this one. The major compromise being made in this system is that we're sharing the ducts for air conditioning, for heating, and for ventilation. So what does that mean when we say we share? It means we compromise. Aren't you the communist socialist guy? You're supposed to jump right in there and say, we compromise so that we can all get along, right? The Rodney King thing that Joe mentioned yesterday. The Rodney King solution is you use one set of ducts, and they're probably a little bit too small for cooling and a little bit too big for heating, and they're way too big for ventilation. And then we come up with some kludge to try and make all of that work, okay? So we use pollutant exhaust at the range hood and at the bathroom fan, because this is a large source of pollutants. We don't have a dehumidifier until we have humidity problems, then we buy a dehumidifier. That's sort of, a thing that'll work. If you're working in the hot, humid climate zones and making efficient buildings, you may as well just go straight to buying the dehumidifier. But if you'd like to, play a little bit of roulette, do the Clint Eastwood thing. So do you feel lucky, punk? Huh? Do you? Just go ahead, just build a bunch of them and see what happens. And of course, I've got domestic hot water tank there in the corner, in the bottom left thing, because of course I do need domestic hot water to be solved as well. So this is sort of, we know we can build inexpensive buildings that work using this system. The challenge is getting the furnace small enough, the air conditioning small enough, and we don't have great efficiency because we don't have heat recovery, but it can all work. But we're going to try and improve on that. So here's an example of improving on that. One, we have a dehumidifier built right in using the same ducts to distribute the dehumidified air. The way you control humidity in a building of any type is that you actually have a device that measures the humidity, and that device is called a humidistat. You might want to write that down. So when people say they control humidity, and there are lots of manufacturers who will sell you systems that control humidity, and they don't measure the humidity, what are they doing? Lying. Now, sometimes they just are idiots and they don't know, but other times they are just lying to sell product. If you're not measuring humidity, it's really hard to control humidity. I mean, it seems like a kind of a given, except this is a conversation we have several times a year with mainline manufacturers. Oh, we got this new system. It's going to control humidity. Yeah, but do you measure it? No. Well, then how the hell are you going to control humidity? So we're starting to break that logjam, and they now are selling thermostats that also have humidistats. Now the challenge is that that device that measures humidity has to control a thing that removes humidity. Okay, it's a major next step. Now, the thing has to be able to remove humidity without making the house cold. Otherwise, if it were to remove humidity and make the house cold, what would we call that? Air conditioner. Right. So the next trick in the manufacturing crowd is that, oh, okay, we measured the humidity now. Yeah. And we got this little two prongs there, 24-volt AC. And when the humidity gets too high, it turns on. Okay, what's it do? Well, it runs the air conditioner. Well, shit, I could have done that. I need something that actually doesn't cool the house down. Duh. Oh, well, mine will work anyway. What do you mean it works anyway? Like, it is cooling or it isn't. And so that's been the, we're actually doing, not making this up. This is true kind of like 5 years of talking to manufacturers about the magics of dehumidification. Maybe more like 10, actually. So we now have RH sensors, but we still haven't quite got humidity control devices because everybody wants to use the air conditioner as the dehumidifier, and no one wants to acknowledge that it produces cold air when it's running, and it doesn't dehumidify when it's not. A lot of really important questions to ask in early design stages, and this is why it's a very standard question design threat. I'm building a school. I want a low energy. Solar heat gain windows with exterior shades. And I got low energy lights so that there's no wasted electricity going into the lighting, etc. Then I put 35 students in that classroom. And they have to get about 20 CFM of fresh air because kids smell twice as much as normal people. They get twice as much air. And so now I have 700 CFM of air being flooded into that room. Okay, so it's 70 degrees and raining outside. Is that a condition that occurs anywhere where you live? Yeah, I'd say it's not an uncommon. Okay, so it's 70 degrees, it's raining, and you're delivering 700 CFM of outdoor air into the classroom. So, will the air conditioner operate when it's an overcast, rainy day and it's 70 degrees outside? There's no heat load. Even 35 kids, their heat's going to be largely removed by that 700 CFM of outdoor 70-degree air. It'll be 74 degrees inside. What's the relative humidity outdoors when it's raining? Let me just picture the moment. There's like millions of tiny droplets of air falling for a mile through the atmosphere. What's the relative humidity outdoors? 100%. So now I'm taking 700 CFM of 100% air, sometimes with the droplets, and I'm dumping it into the classroom. And of course, the thermostat says it's perfectly fine. And now I say, let's add the humidistat. Okay, and add the humidistat. It'll now say, beep, 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 beep. You've got really serious high humidity in the school. Now what are you going to do? Run the air conditioner? Well, if you did, what's going to happen to the classroom? It's going to get cold. And for 700 CFM of 100% air, you'd really have to have a serious-ass air conditioner. That's called a SAAC. That would be able to remove that humidity into safe levels, and to do that, you'd very quickly drop the temperature in that space to 55 or something like that. So of course we can't do that. So what do? Well, we just let the humidity ride. Now, that's an quote-unquote extreme situation in the classroom, but the question in the design stage is always to say what I call the rainy day scenario. What do you do when it's around 70 degrees, raining? How do you control humidity in your apartment, in your house, in your school, in your grocery store? Because you don't need AC, but you need humidity control, and you can't even tolerate even a small amount of cooling without causing discomfort. That's when most systems don't work. So all you have to do is ask the question, rather than build the freaking thing and watch it not work. I can tell you it's not going to work. Okay, so that was about this residential HVAC, is that cooling does not mean humidity control. There is a way to make that classroom or your apartment work. You run the air conditioner, and then what do? Add heat. There really is no real magic. I mean, Andy's written an entire freaking book on this, and you use relatively large print and lots of graphics so that it really should be accessible to like mechanical engineers everywhere, but reading's often a skill that's lost. And so it's pretty obvious that the only thing you can do is add heat. And so the question then, only question remains is where does that heat come from? Do you use a toaster, the most energy intensive form of heat? Or do you use natural gas, or do you use something called reheat from the compressor? Because the air conditioner, when it took the heat out of the air, what did it do with the heat? It threw it outside. Well, shit, that was stupid. When we need heat inside, couldn't we take the heat from that we were going to throw outside and move it inside? I'm a genius. And that's what's called a dehumidifier. It's an air conditioner where it doesn't throw the heat outside, it throws it inside, and so it all works. So we're back to the same solution that we've been to in the last 50 years, but it's been a long and painful process to get people to admit that they have to do that solution. And that process is not done yet. There's still 85% of mechanical engineers we deal with still think that they can control interior humidity without measuring it or having a device that removes it. And that's why we get paid the big bucks to sit on design charrettes. Yeah, that's it. That easy. It's just that easy. Staples thinks they got that button thing. Heck. All right, let's go for a coffee break, smoke break, oxygen break, whatever, and then I'll come back in 15 minutes and start talking about actual devices that do shit.